In this lesson, we're going to apply what we've learned about uncertainty to several practical tasks. So if you haven't seen the first video on uncertainty, please do go back and watch it. We're going to start by using a pipette. Very simply, we're going to remove 14 mils of liquid using the pipette. Then I'm going to calculate the uncertainty and the percentage uncertainty relating to the 14 mils. The large divisions on the pipette are 1 mil. The smaller divisions, of which there are 10 in between, are 0.1 mil. That gives us the smallest resolution of that instrument as 0.1 mil. To get the liquid into the pipette, I've got to use this ball pump. There's several valves on the pump, and if I squeeze the air out of it there and then I press this one, it will inflate and that will suck water up the pipette. We're really careful when we're putting the ball pump on the end of the pipette. We never push it towards us like this. You'll end up with a really terrible accident. We place it on there, make sure it's airtight. Okay, so I'm going to press the valve at the top labelled A, give it a squeeze, push all the air out, there it goes, and then I'm going to place it in the liquid, and then I'm going to press the valve labelled S for suck, and as I do that you can see that the liquid rises up inside the pipette. And there you can see I've gone beyond 0. So now what I need to do is very carefully let some of that liquid out. The easiest way to do this is to remove the ball pump, keep the other end submerged in the liquid, and just use the pressure of my thumb to slowly release. Now I'm using a judgment here. I'm judging when the base of that meniscus has hit the 0. So that's one judgment I've made. Then as I release more liquid to release 14 mils of the liquid into the beaker, I'm making a second judgment. I let the liquid out quite quickly until I get to around 11, 12, 13, and then I'm going to let the liquid move out a little bit more slowly until the bottom of that meniscus is on 14. So thinking about that, because I had to align the liquid with 0 there, and then because I had to align the liquid with 14 there, I've made 2 judgments, and that makes it a measurement. So the smallest division on the pipette was 0.1 mLs. So that means that the uncertainty is going to be plus or minus 0.05 mLs. Now, because we've got 2 judgments, we have to add those together. So 0.05 plus 0.05 is, of course, 0.1. But, of course, this is plus or minus 0.1 because it was plus or minus 0.05. If we want to consider our uncertainty relative to the amount of liquid that we measured, then we're going to work out our percentage uncertainty, which is basically our uncertainty divided by the amount of liquid, our value, which in this case was 14 mLs, times 100, and that gives us a value of plus or minus 0.714%. Moving on, we're going to use a 100 ml measuring cylinder. Very simply, we're going to measure 70 mils of water. Now, in this case, we only make one judgment because we only read at the 70 mark. Here you can see I'm ensuring that the measuring cylinder is on a flat level surface, and I'm lowering my eye to the level where 70 is so I can make sure that the meniscus sits neatly on it. So my resolution is 1 ml. I'm making one judgment. So therefore my uncertainty is plus or minus 0.5 ml. The uncertainty of plus or minus 0.5 ml is related to the instrument. If I want to relate it to the amount of liquid that I have measured, then I'm going to work it out by dividing 0.5 by 70 and times it by 100. And our answer is 0.714, similar to the answer before because we've used very similar numbers. Moving on to our third experiment, I'm using a ruler. I'm going to measure the height of seedlings. The resolution of the ruler is 1 millimetre. To reduce my uncertainty, I'm going to measure the heights of 4 seedlings and take a mean. Now at this point, we're using a ruler. we're making two judgments at the 0 end and also at the other end. And so we know at one end that the uncertainty is going to be plus or minus 0.5 of a millimetre, and at the other end it's going to be plus or minus 0.5 of a millimetre. So that gives us an overall uncertainty for that instrument of plus or minus 1 millimetre. And it turns out that the mean height of my seedlings is 138 millimetres. So if I want to find my percentage uncertainty, again, I'm going to use my plus or minus 1 millimetre divided by 138 millimetres times 100, giving me an uncertainty of plus or minus 0.725%. Now I move on to a digital balance. Here I'm just going to measure the mass of a beaker. I first adjust the feet of the measuring balance to make sure that it's level, and I look from an aerial view and make sure that the air bubble is centered so that I know that it is completely level. I then adjust the mode to make sure that I'm measuring in the correct units and with the correct precision of 0.01. In other words, 1/100th of a gram. All sorted, I place my beaker on top and I write down the result. In this example, I have a reading because I'm only making one judgment. I don't have to worry about the 0 because the manufacturer has ensured that 0 is indeed 0. Now, if the resolution is 0.01 of a gram, then my uncertainty is going to be plus or minus half of that. So my uncertainty is going to be 0.005 of a gram. So that uncertainty stays with the instrument. It wouldn't matter what I was weighing, that uncertainty would be the same. So to relate the uncertainty to the amount of mass that I'm actually measuring, I'm going to work out the percentage uncertainty. So that is plus or minus 0.005 divided by the mass of the beaker, which was 112 grams. I then times that by 100, and I'm not surprised to get such a small uncertainty when I've used such a precise instrument. Okay, so here's an interesting one. I'm going to use the ruler again. Because I'm using a ruler, I have to consider both ends of the ruler, and so it's going to be a measurement. But I'm measuring a change in length. So I'm going to measure before, and then I'm going to measure after. And before you do this, make sure you've orientated your ruler the correct way around. You won't believe the number of times I've seen students measure from the 30 centimetre end. Add the mass and of course the length of the spring changes. After the spring has settled down, of course, make sure your ruler is once again orientated the correct way and measure the new length. Then of course you're going to minus those figures to find the change in length. And in this example, we found that it was 18 millimetres. So this is where it gets interesting. Our resolution was 1 millimetre. Our measurement before used 2 judgments, and then our measurement afterwards used 2 judgments. So in total, we've got 4 judgments to be made. Because our resolution was 1 millimetre, the uncertainty for each judgment is plus or minus 0.5. So our total uncertainty is 4 lots of 0.5. In other words, it's plus or minus 2 millimetres. Again, that uncertainty stays with the instrument for that procedure. If we want to relate it to what we were actually measuring, we're going to use our uncertainty divided by our value, which is 2 divided by 18 times by 100. And the answer, of course, will give us a percentage, but it's plus or minus that percentage, which is our percentage uncertainty. Okay, moving on, we're going to be using a digital thermometer to measure a decrease in temperature of water. So, because I'm using a digital thermometer, it's a reading. I only have to consider one end. I don't need to consider the 0. So I take my reading there. Now the resolution of the instrument is 0.1 of a degree. So therefore the uncertainty is plus or minus 0.05 of a degree. I'm going to shove some ice cubes in that hot water now. I'm going to cool the water down and I'm going to measure the temperature again afterwards. So in total, because I've used before and I've used after, I've got plus or minus 0.05 degrees at the beginning and plus or minus 0.05 degrees at the end. So I've got two judgments together, really. So my resolution is 0.1 degrees. I have a reading, although I have two readings, because I make two judgments, one before and one after. So my uncertainty for the change in temperature is 0.1 degrees C. However, my temperature change was 32 degrees C, so relative to the temperature change, my percentage uncertainty is going to be 0.1 degrees divided by 32 degrees times by 100. Repeating the same experiment with an alcohol thermometer that measures to 1 degree C would follow the same pattern. The resolution is 10 times more, so it's 1 degree C. It's a reading. However, I do the reading twice because it's a temperature change, but because it's just one judgment, it's classed as a reading. So my uncertainty would be plus or minus 0.5 degrees, which gives me a percentage uncertainty, which of course is still plus or minus that percentage uncertainty.